Welcome back to the Deep Dive. Take a look around the world today. Machines are writing poetry, drafting emails, generating stunning images, having conversations that feel, well, surprisingly human.
Yeah, it's everywhere.
It's impossible not to ask the question that feels ripped from science fiction. Could these machines ever actually become conscious? It's maybe the ultimate frontier in AI research, the one that carries the most wonder and maybe the most trepidation.
It really is. It's a question that touches on engineering, yes, but also neuroscience, physics, and even, deep philosophy. Can we actually build subjective experience? Can we, program awareness?
And today we're diving into a paper that doesn't just ponder that question, but delivers a pretty definitive no.
That's right.
We're doing a deep dive into no-go theorems on machine consciousness by Subhash Kak.
From the Journal of Artificial Intelligence and Consciousness.
And the title pretty much gives away the punchline. Using arguments rooted in physics and logic, the paper makes the case that achieving machine consciousness might actually be, well, impossible, a no-go area.
What's particularly fascinating here, I think, is that this isn't just another philosophical debate or, a purely biological argument. Right. The paper takes a bold step by attempting to lay out formal theorem-based arguments for why machine consciousness, specifically, as we often imagine it emerging from complex hardware and software, might be unattainable.
So what's the mission here?
Well, our mission really is to guide you through these arguments, understand these no-go theorems, and figure out what they really imply, not just for building AI, but for our understanding of consciousness itself, and maybe even the fabric of reality.
Exactly. Because, let's be honest, the quest for machine consciousness isn't just about building smarter computers. It touches on huge, almost unsettling questions about intelligence, genuine agency, that feeling of actually making a choice, and ultimately what makes us, us. And as we'll see, this paper doesn't shy away from connecting these ideas to some of the deepest, strangest paradoxes we find when we try to put consciousness into the equations of physics.
Yeah.
This is where it starts getting really interesting.
Okay, let's dive in.
And hey, while you're diving deep with us, please do take just a second to like and subscribe. It really helps us keep bringing you these explorations into the most intriguing corners of knowledge.
It does, thanks.
Okay, let's unpack this extraordinary claim. So the paper kicks off by establishing a concept that seems straightforward enough on the surface. The idea of a causally closed physical world.
Okay.
Think of it like a perfectly sealed system where every physical event that happens inside is caused by other physical events already within that system.
Right, so no outside interference, just physics following physics, cause following effect in a predictable chain, like clockwork, basically.
Pretty much.
And this is where the paper immediately highlights a profound tension. If our physical world, including our brains and bodies, is strictly causally closed, like a giant clockwork mechanism, then where does something like free will or genuine agency fit in?
Good question.
Conscious agents, like us, we seem to act from a place of choice, initiating actions that aren't simply the inevitable next step in a predetermined physical chain.
Yeah, it feels like we make choices.
The paper argues this apparent freedom, this capacity for choice beyond just chance or necessity, is a key feature of consciousness, and it immediately bumps up against the idea of a purely causally closed physical system.
Right. It's like if every thought and decision you make is just the inevitable physical output of the state of your brain microseconds before, dictated by the laws of physics, are you really making a choice?
Or are you just following a complex physical script? It's a deep philosophical problem.
And this connects to another deep problem, the role of the observer. Classical physics could largely ignore you, the observer. A planet orbits a star whether you're looking or not.
Sure, seems obvious.
But quantum physics, suddenly, the act of observation, of measurement, becomes central. It seems to, collapse possibilities into reality.
The measurement problem, yeah.
But quantum mechanics still doesn't explain how this observer, who does the collapsing, this conscious entity, arises from the physics in the first place. It treats the observer differently, somehow.
And this is the critical link to the AI question, isn't it?
How so?
Well, the paper asks, can an AI machine operating purely on physical hardware, following physical laws and executing algorithms, ever possess this kind of agency? This capacity to observe and choose in a way that isn't just the predetermined outcome of its programming and inputs.
Right. Is consciousness something that can simply be computed or simulated?
Exactly. Can you code awareness?
Which brings us to the core logical structure of the paper. It asks us to imagine systems nested within other systems. Picture a large physical system, let's call it S.
Okay.
And within S, there's a part that acts as a cognitive agent, C, you could think of S as the universe and C as a person.
Or S as a computer and C as an AI program running on it.
Exactly. The agent C observes things happening within S.
Now, the paper identifies a potential logical conflict if you assume S is causally closed and C is a truly conscious agent with agency.
Yeah, walk me through that.
If S is causally closed, then the state of everything in S, including the state of agent C, what it's observing, what it's thinking, is fully determined by S's previous states. C's observation is just part of this physical progression within S.
Makes sense so far. It's all just physics happening.
But if C has genuine agency, if its observation or a choice it makes could somehow initiate a physical effect in S that wasn't entirely predictable from the prior state of S alone, introducing something genuinely new.
Oh, I see the clash.
Then it breaks the causal closure assumption of S. It's like a character in a movie script suddenly deciding to do something the script didn't dictate, and it actually happens in the movie's physical world.
That would mess up the whole plot's causal chain.
Exactly. You can't have both perfect causal closure for the whole system and truly independent agency for a part within that system.
And this logical puzzle leads directly to the first no-go theorem. Theorem 1. Nested observers cannot exist.
Okay, nested observers.
Now, let's translate this for AI. The paper argues if consciousness is something that simply pops out of physical complexity, like if your brain's consciousness comes from the complex interaction of neurons, or an AI's consciousness would come from the complexity of its code and hardware.
Which is a common assumption, right? Emergence from complexity.
Right. Then you'd essentially have conscious agents potentially nested within other systems that are themselves being observed. Think of subsystems in your brain or layers in a neural network. The paper argues that if you have a superior observer looking at the whole system S, which contains C, and C is supposed to have genuine agency within S,
then C's free actions would mess up the superior observer's ability to describe S as a simple, causally closed system. The descriptions would conflict.
Because C's actions wouldn't be predictable just from S's prior state if C has real agency.
Exactly. The key insight here is that if consciousness is merely an emergent property of a physical system's complexity, and that system is part of a larger, causally closed universe, then the agent C is fundamentally just a determined part of S.
Any apparent agency is just an illusion from that higher perspective.
From the perspective of a comprehensive observer of S, yes. Trying to assign genuine agency to C while maintaining S's causal closure for a higher observer creates a logical contradiction.
So you can't just stack complexity.
It suggests that you can't just layer complexity, expecting conscious agents with independent agency to appear at each level within a causally closed framework. The logic seems to forbid it.
Okay, so the crucial takeaway from Theorem 1 for AI is this. If consciousness is just complexity, you can't simply build complex AI systems with nested structures and expect true, independent, conscious agents to emerge seamlessly within that physical computational system.
Not if the whole setup is meant to be causally closed, which is how we usually think about physical systems, including computers.
Okay, wow, that's a big hurdle already.
Which naturally scales up the problem. If this conflict exists for systems within systems, what happens when we consider the largest possible system?
The entire universe. Right. That brings us to the second theorem, Theorem 2. There can only be one observer. The reasoning extends the nested observer issue. If we consider the entire universe as one vast, causally closed physical system, the ultimate S,
then to avoid the logical contradiction of nested agents with conflicting descriptions or influences, there could logically only be one truly conscious agent, the ultimate C, within that single closed system.
Okay, hold up. But that's clearly not right, is it? I mean, we know with pretty high certainty that there are many conscious agents out there. Look around. Everyone listening right now.
Yep, that's the elephant in the room. Billions of us.
How on earth does the paper square this one observer theorem with the undeniable reality of multiple conscious beings?
This is perhaps the most speculative, but also maybe the most mind-bending part of the paper.
I'm ready.
To resolve the conflict between the one-observer theorem and the existence of multiple observers, the paper suggests that perhaps consciousness isn't a physical property that exists inside our familiar space and time at all.
Whoa, okay, outside of physics.
Or at least not part of the causally closed physical description. Instead, it might belong to a fundamentally different dimension or realm, one that interacts with the physical world, but isn't of the physical world in the same way.
Okay, so consciousness is somewhere else.
Yeah.
But how does it interact without, breaking the rules of physics or violating causal closure entirely. That seems like the original problem again.
That's the key question. And the paper proposes something subtle. It suggests this non-physical consciousness might interact not by applying physical forces or changing physical states directly.
Like pushing atoms around.
Right, not like that. But by subtly influencing the probabilities of outcomes in the physical world.
Influencing probabilities. How?
It draws an analogy to the quantum Zeno effect, a weird phenomenon where if you constantly observe an unstable quantum particle, you can actually prevent it from decaying. Frequent observation seems to freeze the state.
I've heard of that. The watch pot never boils, quantum style.
Kind of. The idea is that consciousness might work on probabilities, gently nudging the likelihood of certain physical events without violating the fundamental conservation laws or causal chains that describe how energy and momentum flow. It interacts with the possibilities, not the certainties.
Fascinating. So it's not a ghost in the machine pulling levers, but more like a probability whisperer.
That's one way to think about it, yeah. It's a way to potentially allow for agency without breaking the established physical dynamics.
And this loops back to the idea of complexity not being enough, right? This feels very different from just complex calculations.
Exactly, and that's articulated in Theorem 3. Consciousness associated with cognitive agents cannot be emergent on the complexity-based hardware.
Okay, this sounds like the core AI argument.
It really brings the argument squarely back to AI. If consciousness were merely a physical process arising from complexity, like a really complicated calculation...
Like the algorithm that powers a neural network, no matter how big.
Precisely. Then it could, in principle, be fully described by a mathematical algorithm.
Makes sense. You could write down the steps.
And the paper argues that algorithms, by their very nature, follow a predetermined sequence of logical steps. They transform input into output based on predefined rules. They don't create anything fundamentally new.
What do you mean by new?
The paper contends that such algorithmic processing, however complex, fundamentally lacks the capacity to generate a truly new phenomenon, subjective, unified, conscious experience. Qualia. The feeling of what it's like.
Oh, it's just manipulating information according to rules.
Yes. It can simulate intelligence or even emotion based on patterns it learns incredibly well, perhaps, but it can't be the subjective experience itself. It can describe red, but it can't see red. The paper even cites research suggesting complexity-based consciousness models, if they can be reduced to algorithms, might actually be outside the realm of empirical science because they predict nothing fundamentally new that isn't already implicit in the algorithm itself.
Okay, so Theorem 3 is a direct shot across the bow for the idea that if we just build a really, really complex AI, consciousness will just emerge naturally from the intricate wiring and computations.
The paper says, nope, algorithms don't do that. Not in this view, anyway.
But isn't our own brain just incredibly complex biological hardware running electrochemical processes? Couldn't that be mapped to an algorithm, at least in theory? That seems like a common assumption in neuroscience and AI.
That's a great question, and it gets to the heart of the matter. This paper suggests that the conscious aspect of what happens in our brain isn't the part that can be mapped to an algorithm.
So what is algorithmic then?
The computational stuff, memory, learning, pattern recognition, decision-making based on input, that's the algorithmic, the mind in their terminology. But the awareness that experiences these things.
That's the non-physical light the paper proposes.
That seems to be the idea. The awareness itself isn't the computation. It's what experiences the results of the computation.
Okay, to really understand why the paper leans so heavily on this idea that the observer is special and maybe separate from the physical system, we need to dip our toes into the truly bizarre parts of quantum mechanics.
Oh boy, here we go.
Where the observer isn't just problematic, but a central mystery. The paper highlights two famous quantum paradoxes that illustrate this issue: Schrödinger's cat and Wigner's friend.
Yes, the classics. Gotta talk about the cat.
Let's start with Schrödinger's cat. You've probably heard this one. Put a cat in a box.
With a tiny bit of radioactive material, a Geiger counter, a hammer, and a vial of poison. A terrible setup for the cat.
Right. If the material decays, a quantum event, the Geiger counter clicks, the hammer breaks the vial, the cat dies.
And according to quantum mechanics, the radioactive atom can be in a superposition, both decayed and not decayed at the same time until it's observed or measured.
And the paradox is that because the cat's fate is linked to the atom, standard quantum logic seems to imply the cat itself is in the superposition of alive and dead simultaneously until you open the box and look.
Which is absurd.
But when you open the box, you never see a half-alive, half-dead cat. It's always definitely one or the other. So the paradox asks, where is the line? When does fuzzy quantum possibilities snap into definite classical reality?
Does a cat count as an observer that collapses the atom's state? What about a Geiger counter? Or does it take a conscious human?
Exactly. These are the questions. Now, what does the paper say about this? Does it solve the cat paradox?
Well, the paper's analysis here is quite specific. It argues that, according to the author, the Schrödinger's cat scenario as a true quantum paradox causing macroscopic superposition is often misunderstood. It argues there's no paradox in reality for the cat itself.
How so?
Okay, a few points from the source. First, it questions whether the setup truly creates the kind of quantum entanglement needed to force the macroscopic state of the cat into a genuine alive-dead superposition. That linkage might be flawed.
Okay, maybe the connection isn't perfectly quantum.
Second, and more crucially, the state of the cat being alive or dead is fundamentally a classical property. It's not like a particle spin where you can measure it along different axes and get different superposition results.
Right. You can't measure a cat's aliveness in different quantum bases. It's just alive or dead.
Exactly. You can't perform a quantum measurement on the cat to reveal its supposed quantum superposition of being alive and dead. Its state is always definite from a classical perspective.
So the problem is mixing quantum rules with classical objects.
That's the argument. The perceived paradox arises from incorrectly applying the rules of quantum superposition, which govern quantum variables, to the macroscopic classical state of the cat. The state inside the box, in this view, isn't a quantum superposition of macroscopic states, a live cat plus dead cat.
What is it then?
It's more accurately described as a classical statistical mixture. There's a probability the atom decayed and the cat is dead, and a probability the atom hasn't decayed and the cat is alive. When you open the box, you're just finding out which classical outcome occurred. You're resolving ignorance, not collapsing a macroscopic superposition.
Okay, so in this view, the cat paradox isn't really a paradox about consciousness collapsing the wave function, but about trying to apply quantum weirdness where it doesn't fit to the macroscopic classical world. Got it.
It sidesteps the need for the cat or consciousness to do the collapsing at that macro level.
But then there's Wigner's friend. This one feels more direct because it involves two people, two consciousnesses.
Right. This is a variation proposed by Eugene Wigner, a Nobel laureate. Imagine a physicist, F, the friend, is inside a sealed lab and measures a quantum particle, say its spin.
Okay, friend measures the spin. It's up or down.
For F inside the lab, the particle's quantum state immediately collapses to a definite result, say, spin up as soon as they measure it. They know the outcome. They've experienced it.
Right. Measurement happened. Reality chose.
But outside the lab, Wigner, using standard quantum mechanics, describes the entire lab system, including F, the particle, even F's brain state reflecting the memory of the result, as still being in a quantum superposition of all possible measurement outcomes.
Wait, so Wigner sees the lab as both friend-measured spin-up and friend-measured spin-down at the same time.
Until Wigner himself interacts with or measures the lab system, yes. According to a straightforward application of quantum mechanics to the whole lab as one quantum system.
And the crunch is, F and Wigner have legitimately conflicting descriptions of reality at the same time. F insists the particle spin is definitely up, while Wigner's quantum description says the lab, including F's definite knowledge, is still in a fuzzy state where both outcomes are superimposed?
It's a real clash of descriptions. Whose reality is correct? Does F's consciousness collapse the state only inside the lab? Does Wigner's collapse it for everyone?
This paradox powerfully suggests that the standard rules of quantum mechanics might break down, or at least become inconsistent, when you try to apply them to systems that include conscious observers.
Exactly. It strongly implies that a conscious observer isn't just another physical system that you can include in a quantum description in the same way you would a particle or a rock.
The act of conscious observation seems to play a unique role, maybe a boundary effect.
It seems to break the chain of quantum superposition, forcing a single classical outcome.
And this is the foundation for the paper's fourth theorem, right? Theorem 4. An observer cannot be part of a quantum state.
Yes, although it's presented more as a conclusion drawn from the inconsistencies highlighted by these paradoxes and other scenarios, rather than a formal mathematical proof within the paper itself.
So it's like a theoretical boundary proposed, because trying to put a conscious observer into the quantum description just leads to contradictions like Wigner's friend.
Precisely. It reinforces the idea that there seems to be a fundamental distinction between the realm described by quantum mechanics, superpositions, probabilities, possibilities, and the realm of conscious experience, definite realities, single outcomes.
The conscious observer seems to exist, or at least function, on the side of definite classical reality, interacting with the quantum world in a way that causes its possibilities to solidify.
That's a good way to put it. They bridge the quantum and the classical, in a sense not fully explained by the physics itself.
Which circles us back to the brain and consciousness research in neuroscience.
Yeah.
Because many prominent theories today do try to link consciousness directly to the physical complexity and specific dynamics of the brain.
Right. You have theories like recurrent processing theory, RPT, focusing on feedback loops.
Or integrated information theory, IIT, trying to quantify consciousness based on how integrated the information flow is in a system, like the brain, or potentially a computer.
And these theories fundamentally see consciousness as a product, an emergent property of complex physical brain activity.
So how does the paper critique these? Because they seem like the main alternative to this non-physical view.
The paper offers a direct critique, bringing in Theorem 3 again, the one about algorithms. It argues that because these neuroscience theories rely on mapping consciousness to structural complexity or information processing within a physical system,
they can be described mathematically.
They can often be reduced, in principle, to mathematical algorithms or computational processes. Even IIT, with its complex phi measure, is ultimately based on the causal structure and information processing of the physical system.
And as Theorem 3 argues, algorithms don't create consciousness.
Exactly. Therefore, from the paper's perspective, these complexity-based theories of consciousness might be fundamentally misguided. Or perhaps they're only describing the physical correlates of consciousness, the brain activity that happens when consciousness is present rather than consciousness itself.
So they're mapping the shadow, not the thing casting it.
In this view, yes. It doubles down on the idea that if the theory maps to an algorithm running on hardware, it's describing the mechanism of the mind, but not the subjective awareness, the light.
So the paper's alternative view, pulled from all these arguments, causal closure, nesting, the one observer, quantum issues, algorithms, is really quite distinct.
It is. Consciousness is not seen as a physical process happening in the brain. It's not localized to specific brain regions in a static way.
You mentioned the paper references this idea of the self dancing through the brain.
Yeah, drawing on work by Samir Zeki suggesting the focus of awareness, the sense of self, seems dynamic, shifting between different brain networks as needed, which reflects that it's not pinned to one physical spot. It uses the brain, but isn't in any one part of it.
And crucially, it's not something that simply emerges from physical complexity or computation.
Summarizing the paper's perspective, then, it views consciousness as a non-physical light or awareness that illuminates the contents of the mind.
And the mind itself is physical.
Yes, the mind, in this view, is physical. It's the brain's machinery handling memory, ego, the sense of self as a physical biographical entity, intelligence, problem-solving, learning, etc. These are all complex, physical, arguably computational processes.
But consciousness is the unified, non-physical observer of these physical contents. It's the screen onto which the physical mind projects its movie.
That's a fair analogy for this perspective. And the paper notes this kind of view resonates with certain ancient philosophical traditions, particularly Vedanta from India, which makes similar distinctions between the physical apparatus and a non-material awareness.
Wow, okay. That's a lot to take in. So what does this all mean for us and for the whole field of AI? Let's try to bring this landing.
Let's try.
The paper by Subhash Kak lays out a series of powerful, logical, and physics-based arguments, these no-go theorems, that suggest there are fundamental barriers to creating machine consciousness, if consciousness is what we think it is, and physics, especially quantum physics, works the way these arguments interpret it.
Right. It starts with that logical problem, trying to squeeze genuine agency into a strictly causally closed physical system.
Which leads to the argument that you can't have nested layers of conscious agents emerging just from complexity within such a system.
That then scales up to the provocative one-observer theorem for the whole universe.
And the paper's suggested resolution for that involves consciousness perhaps being a non-physical dimension influencing probabilities, not forces.
Then it directly targets the idea that consciousness emerges from complexity or computation, arguing that algorithms, by their nature, just manipulate information according to rules and can't create a genuinely new phenomenon like subjective experience.
And it uses the strange inconsistencies we find with the observer in quantum mechanics, highlighted by paradoxes like Wigner's friend, as evidence that maybe consciousness isn't just another part of the physical system being described, but something distinct.
Mm-hmm. Put it all together, and the paper's main conclusion is stark. Based on these no-go theorems, consciousness is not a material property that simply emerges from the kind of physics we use to build computers.
Which means?
Therefore, AI machines of the future, built entirely on physical hardware and algorithms, will likely never achieve consciousness in the same sense that we possess it, at least not according to this specific line of reasoning.
And that's a pretty profound implication, isn't it? Not just for AI researchers hoping to spark genuine awareness in their creations, but for all of us.
It really is.
This paper presents a rigorous, albeit potentially controversial, challenge to the widespread assumption, or maybe hope, that building a sufficiently complex machine will automatically grant it subjective experience.
It forces us to step back and ask those deep questions again. What is consciousness really? Is it just a complex computation, or is it something fundamentally different?
This perspective, drawing on deep wells of physics and logic, offers a powerful reason why the answer might be the latter. It's certainly food for thought.
A lot of food for thought.
So here's a final thought for you, the listener, to carry with you. If consciousness, as this paper suggests, is not a physical thing that just pops out of complexity, if it's more like a non-physical light that illuminates the separate physical workings of the mind, memory, intelligence, ego, what does that distinction truly mean for AI? Are we building AI that enhances the physical mind, making it smarter, faster, better at processing information, pattern recognition, problem solving? Or are we mistakenly chasing the non-physical consciousness itself, perhaps down a path that physics and logic, according to this paper, might suggest is a dead end?
It really reframes the goal, doesn't it? Are we aiming for superintelligence or subjective experience? And this paper argues those might be two very different, maybe even incompatible targets using our current methods.
It's a question that sits at the intersection of everything we understand about the universe and ourselves. This paper is just one rigorous perspective in that ongoing exploration.
Absolutely. But it's one that certainly gives you pause, makes you think hard about the foundations. There's always more to ponder, more to investigate.